Hi there, I'm Han. This is just another video of me solving random code problem. So today we have the game of life. Um, so we just have a grid, right, with 0 and 1. That's it. 0 is dead and 1 is life. So any life cell, we need to iterate over each cell and then apply this rule, right? So if a life cell with fewer than 2 neighbors, right, we die because underpopulation. Right? If a cell more than 3, um, also die because overpopulation. Right? If it has 2 or 3, that is live on. So if it is less than 2, right, uh, or greater than 3, right, die. So that is a life. This is for the life cell, right? Life cell 1, right? And for the dead cell, only one rule for the dead cell. The dead cell uh, 0, right? The dead cell is with exactly 3 neighbors, leaf uh, the neighbor become a leaf cell by reproduction. Right. So if you look at the 0 here, right, it had 3 neighbors, exactly 3 neighbors. Neighbors is considered the live neighbors, right? You have 3 live neighbors. So we only care about the live neighbors here, right? So if had exactly 3 live neighbors, so in the next state, this become alive again, right? By reproduction. So we always consider the live neighbor here, right? Which is 1. We don't care about the dead neighbors. So pretty straightforward, right? Our neighbors will be in a direction, right? We need a hyperfunction to generate the neighbors. So the problem that we have now, so first of all, we can do this in O of n by n, right? Time and also space, right? We have to create a copy of the board to do this, right? Because for example, if we change it in place, right? If we change it in place, if we change this could become a 1, right? And the rules change, right? We want to uh we want to create the next state of the board, right? Based on the previous state, right? If we mutate the state, then it will change, right? Right. So for example, if we iterate to this cell, right? So we know that okay, this cell become 1, for example, right? So when we look at the last cell, right? The last cell supposed to have 2 live neighbors, but now it have 3 live neighbors because we added it in place, right? So now this also become a 1 because it have exactly 3 neighbors, which doesn't match with what we have here, right? So that is one example. So we can do this in O1 space by using a little trick. So we just have to um re re remember the previous state of the cell, right? So for example, we can say that okay, any live neighbor is the live neighbor, right, can be the live neighbor will be any number that is greater than 0, right? 1 is greater than 0, but 2 is also greater than uh than 0, right? So actually we can uh mark it as number 2. We can use like any positive number other than 1 here. I can use 2, right? 2 mean the cell is previously alive, right? And I can use a negative number to represent the dead cell, right? Because we already use 0 and 1. Um, -1 means like the cell is previously, right? So it is dead in the previous state. Okay, so let's look at this example here. I can turn this one into a -1, right? So we know that this number, right, is previously this number is a zero, a dead cell, right? -1 means the cell is previously dead, right? So when we look at this cell, when we call our get neighbor function, it's only return 2, right? Because why? Because we are the neighbors are only the one with the values greater than 0, right? So the -1 doesn't count. So the 0 here will stay at 0, right? Similarly, let's see, if it's less than 2 neighbors. Okay, so let's look at the one right here, right? Because it has less than 2 neighbors, 2 live neighbors, it's only have 1 here, right? So it will become 0 at for the next stage, right? So instead of writing 0, right, we can write 2 to indicate that 2 mean, okay, to indicate that the cell is previously is a live cells, right? It's a live cells. So after we did that, we can just iterate through the whole board again and turn any 0, right? 0 to 2, 2 to 0, right? And -1 to 1, right? Right. So the point here is that we use a positive number other than 1 and 0 to represent the previous state of the cell, which is alive. And we use a negative number to represent the state of the cell, to represent the previous state of the cell, which is dead. Right? So actually, we can walk through an example here. So we can look at every cell, right? It is 0, the 3 neighbors, right? So one have less than one than than, uh, than 2 neighbors, right? So it's dead. So we turn it into a 2, right? Look at 0 here. Only have only have 2 neighbors, right? Because neighbor mean positive numbers, right? 0 here only have 2 neighbors. Oh, sorry, the 0 have 3 neighbors, right? This one, this one, this one, 3 neighbors. So it become a 2, right? Um, Same here. The 0 here has 1, 2, 3, 4, 5 neighbors. Wait, sorry. I think I made a mistake. So because it is a dead cell, right? Um, because it is a dead cell, it is not a live cell. It's just my bad here. So because it is a dead cell, the only rule for the dead cell is that it needs exactly 3 live neighbors to become alive, right? And it have exactly 3 neighbors, right? So we turn this into a -1, right? Not 0. Because -1 is to represent the previous state of the cell, right? Which is that, right? Which is the 0 here, right? So -1 here. So look at the next 0 here. It has how many neighbors? 1, 2, 3, 4, 5, right? Not exactly 3, so we just say 0. Look at this one. It has 1, 2, and 3 neighbors. So it is live on to the next generation, right? Okay, and then we look at the next one, the one here. It has only one element. Sorry, one neighbors. So it become dead, right? So we can use a positive number to remember the previous state of this cell, right? Okay. The next one is 1. It has 1, 2, and 3 neighbors, exactly 3. So it live on to the next generation, right? 1. It has only 2. How many neighbors? Let me see. So 1 and 2. Yeah, 2 neighbors. So it live on to the next generation. Yep. The 0 here only have two neighbors, right? So nothing changed. The 0 here, right? 0 here have exactly three neighbors. So it become alive again. So and we use a negative one to represent a dead cell, right? And the 0 here only have two neighbors. Right? So it just stay the same. So now we are finished, right? We're finished. We modify everything in place and we are finished. So now we can iterate through each cell again. And if it is a 2, we turn it into a 0. Okay. If it is 2, it becomes a 0. And if it is a negative one, it becomes a 1. 1. Okay. And that match with what we have over here, right? Okay. So we can achieve constant state using that strategy. So yeah, let's begin to code this up. So we need our neighbors function, taking the row in the column. We can return the neighbors. We can have our direction here. We have the neighbors in a direction, right? So negative 1, 0, 0. Yep. Okay. So we need to map it. So this is dx and dy, right? Delta x and delta y. So our new possible new position will be row plus dx and column plus dy. And after we map it, we need to future it, right? So this is new x and new y. So new x has to be less than number of rows. New y needs to be less than number of columns, right? So we need to create a few constant here. Rows equal to border blank. So columns equal to board 0 blank. So and x needs to be greater than or equal to 0. Also, and y needs to be in bar, right? And then we have to make sure that it is a positive number, right? The cell, we only care about the live neighbors, right? So actually, let's make it super clear. We only care about the live neighbors. So we can do live neighbors, right? And we can do put board right at the row, at the new row, right? New x and the new y, right? Reset them to, right? And we only interested in the length, right? We only interested in the number of neighbors here. So we can return only the length of what we have future out. Okay. Um. So now we need to iterate through each cell. Okay. And we have two cases, right? The first case is when any cell. So the first case is for the live cells, right? So if we have a live cell row and column, right? If it is a live cell, which means it is a one, it's only die if it is under population or overpopulation, right? So if the number of neighbors, so we need to get live neighbors equal to live neighbors, considering the row and the column, of course. If the live neighbors is less than 2, or the live neighbor is greater than 3, we can return. Sorry, we uh, can set it to a positive number, set it to 2 to represent the previous state of the cell, right? The previous state of the cell is a positive number, a live cell, so we set it to 2. And else if uh board row and column, if it is a dead cell, right? And it need exactly 3 neighbors to turn into a live cells. Um, and we need to use a -1 to represent the previous state of the dead cell, right? And two to represent the previous state of the live cell. So it again, if it is a live cell, right, we only turn it into a 0, right? If it is overpopulation or underpopulation. And if it is a dead cell, it become a lie on if and only if the number of neighbors equal to 3. Okay, and that's it. So after that, we need to iterate through the board again and turn any 2 into a uh, if, so the 2 will become a 0, right? And the -1 become a 1. Right? And we don't have to return anything. Um, so actually, we should give the 2 and the -1 some constant, right? To make it even clear for readability. So we can name the 2 is previous state is life, right? And then previous state is dead. Right. So previous life and uh previous death. Okay. So let's try this. And it worked. Thank you for watching.